afternoon. I am so happy to be here. Hello, I'm Leslie Field. I have the privilege today of sharing with you a well-founded hope, a hope that's the result of a dozen years of diligent work, that we can restore the Arctic, thus giving us the time that we need to do all the hard work of decarbonization that we've been hearing about for the last couple of days. Like you, I have always loved nature. I love hiking in it, hearing the wind and the water, sometimes being called to paint it. And I just love the natural world, being in it, hearing it, seeing the thousand shades of green. It's unimaginably rich. Who here hikes? I assumed yes. Who loves wildflowers? And who has kids? Right. We're all in this together. And because I'm a concerned mom, there's one. Such a good cue. Who, like you, worries about the people we love, right? The people I love, the people you love. I decided to take climate change on. In fact, I've been at this since seeing the Gore movie in 2006, The Inconvenient Truth, when my kids were 6 and 10 years old. I decided to bring my skills as a PhD engineer to bear, with degrees from MIT and Berkeley, to bear to build a team and a solution to preserve this beautiful world for future generations. You don't need any more depressing slides, but here's one. It's the only one. We've gathered here today because we feel called to act. It is so urgent, this situation here, as climate becomes more and more unstable. And as we all have heard abundantly here, this isn't some problem for 2100 or someplace only far away. It's right here, right now, with these unimaginable impacts all over the world. Floods, sea level rise, devastating wildfires, which you feel very personally here. We do too, from the Bay Area. I mean, it's just, and climate refugees already at huge levels, which is only going to get worse if we don't get this changed. It's terrible. And unless we take some decisive and large action right now, immediately, it's going to get a lot worse. So Arctic sea ice turns out to be, yes, as you say, turns out to be ground zero for climate change. The Arctic, and the Arctic sea ice in particular, the Arctic is heating much faster than the rest of the world. Shown here is that from 1985 to 2018, we have lost 95% of the multi-year ice in the Arctic. This is something NOAA came out with just in December. That heat shield that we've had in the Arctic for the last 700,000 years is gone. And this is a lever on many of the other climate effects that we've just been talking about for the last couple days. This is worsening all of it as we destabilize the jet stream, as we've lost that reflectivity that we need so much in the summer when the sun is shining up in the Arctic 24 hours a day. So let me show you this relentless decline, again from NOAA, of the ice in the Arctic. I wish I had a pointer here, but follow along. Multi-year ice is light blue here and white. Newer seasonal ice is shown as dark blue. Open ocean is black. And here's the Beaufort Gyre being illustrated just for a second there. That was the historic bright white shield there on the lower left. Used to be a large reservoir of bright reflective ice. And then see the ice flowing out through the Fram Strait next to Greenland. You can see how much worse things have gotten in just the last few years. There it went. So this is an astounding video. And it's not been as much realized worldwide as you might think until very recently. The overall change in ice snow albedo in the Arctic could add as much as 50% to the direct global heating effect of CO2. This is a quote from Professor Peter Wadhams, who is one of the revered ice polar researchers in the world. He's an expert. He's on our scientific advisory board. And just think about that. CO2 is only part of what's driving global warming now. It drove the loss of this ice and snow, but now this loss of reflectivity in the Arctic is driving more. So it's an accelerant for us. So make no mistake, we've still got to get a handle on CO2 despite this new and large other lever that's driving massive climate change now. But here's the thing. Restoring the Arctic would buy us some time, some additional time with less devastation to take on all the rest of that hard work on CO2 that we know we need to do. And the reason I'm talking with you here today is that we have a solution to restore Arctic ice. So we can restore the Arctic's reflectivity, and here's how. One way is to find a material that would be safe enough to, when put on top of young, thin, not very reflective ice, could make it act like more reflective ice. And we need a safe material, a material that would not cause other harms. One of our first principles, you'll hear it a couple times, is first do no harm. We've really looked very, very hard to find the safest material we can get. This particular material is our current favorite. It's hollow glass beads. Glass is mostly silica. And let me make the distinction. I have loved these plastic talks during this conference. Plastic has so many problems. When we chose a material here, we deliberately chose one that was not plastic. Thank you. Indeed. It is, in fact, in many ways, the unplastic. A, it works better. We're not going to suppress evaporative cooling. Okay, here goes the nerd in me. But B, we're not going to be attracting oil-based pollutants, breaking down, getting eaten at the bottom of the food chain with attendant poisons. No, silica. This is basically silica, sand, and it, thank you, and it has been, we've all evolved with it. Silica is safe. It's in my vitamins. It's in just about everything. This particular material is everywhere. It's used in building materials to make them lighter and less thermally conductive, medical applications, paints and to brighten paints for cool roof type applications, and marine engineering applications. They're low cost, they're commercially available. Here's how it works. We're looking at restoring the reflectivity of ice. You can see on the left here, left as you see it, open ocean reflects almost nothing. Thin ice reflects more. Go over to the far right, multi-year ice reflects far more with snow on it, gets even better. In the middle there is that thin ice with young ice with a thin layer of hair's widths of this bright reflective material, and it acts a lot more like multi-year ice. We can restore the reflectivity of the ice. And restoring the Arctic sea ice is a crucial lever on climate change that's achievable right now. So the well-founded hope here and a bit more time can let us have the courage, the will, the hope to decarbonize the economy like we need to, turn over the infrastructure. And in the work, yes, let's be sure we first do no harm. Let's rebuild a natural process. Let's do the most with the least intervention, and let's always work with transparency and permission. It's what we do every day. Just a thin layer in field testing on a lake in Minnesota. You can see we've got additional brightness where we've spread our material compared to the intrinsic ice. And we increased the reflectivity by at least 50% and made the ice last longer by at least 20%, which can help us restore Arctic sea ice to give us time to stabilize the climate. In fact, what we have found is, over our 12 years of field testing, this is shown up our Arctic test site up in Barrow, Alaska, as far north as you can go in the US. On the right, we have found the groundbreaking thing, working with climate modelers, expert climate modelers, that just this humble delay in ice melt can actually restore the ice in the Arctic. So shown here, right, it's a profound result. Wow, beyond what I had dared to hope. So on the left-hand side of the modeling pane here, you can see what the world is like without doing any intervention in the most optimistic scenario where every target from the Paris Agreement was met. And we've got a little bit of ice. But on the right side, with this sort of reflective treatment, we're finding a profound restoration of Arctic ice. So this is in the peer-reviewed literature now. We do the testing, the permitting, the validation, partner with the modelers and do the modeling, and share our work with the scientific community, and we are the farthest ahead Arctic restoration in the world. Thank you. Yeah, thank you. I don't say that lightly. It takes a dozen years of work to become an overnight success, I think. We also don't need to carpet the Arctic, which is tremendously important for cost and logistics and all. What our climate modelers are working on now is that Fram Strait that I pointed out to you is so key. If we can increase the reflectivity there, we can actually tip the balance. And so a key area like that has 10 times at least more impact per unit area than trying to do an Arctic-wide deployment. NASA is now helping to provide resources to power our climate modeling to get the rest of the story so that we know what month, what area, all of the things that we need to know. We could, with the right permissions and funding, start restoring Arctic ice by 2022. But we can't do this alone. What does the work cost? That's part of the key. We need the permissions, we need the money, right? Basically, it really is true. An ounce of prevention is worth a pound of cure. These vertical bars here aren't even to scale because you wouldn't be able to see the cost of the 10 million per year for the next 3 years that we need for our R&D on this massive scale. To the right is shown the $1 to $5 billion a year it would take to do this at scale, in these strategic areas, once we have partnerships with the UN, permissions from the International Maritime Organization, the things that we need that we hope that you can help make connections for us with. Referrals at ice911.org is a good way to tell us key partnerships that you would have in mind, or just write to any of us. We've got a number of members of the team here today, and we'll be around. And so on the right, you can see compared to that just single disasters, $65 billion to clean up Superstorm Sandy, $400 billion worth of disaster, of lost economics, of trying to clean up from the California wildfires just here last year. Single events, really, all over the world. But if you sum them all up, you're in the trillion-dollar type levels that people have been talking about, right? So this is what we need to do. We need to get to work, scaling the field testing, getting the permits we need, scaling the climate modeling, helping the regulators to develop the governance framework so that we can get these key permissions, scaling the funding, getting the international support for deployment. We would love to work abroad as well. It might go a little faster than the permissions that we have been filing with our own EPA here. And slow the devastation, give the world time to decarbonize and restore the Earth's heat shield. So I invite you to join us in this movement of hopeful action to restore humanity's future. And ask yourselves, if not all of us here, who? And if not now, when? We'd love you to join us in helping to create a brighter future for the world. Thank you.
So your technologies are pretty mind-blowing. At least they were for me. And I know that it's hard to absorb all of this in a very short presentation. So I'm hoping that we can start things off by digging a little bit deeper and understanding a little bit better how your technologies work. Leslie, I'd like to turn it over to you for a minute. Your technology sounds straight out of science fiction. Can you tell us a little bit more of a little bit more about the chemistry and the physics of how the product works, right? And how this small change in reflectivity can really have such a big impact?
Yeah, the question I asked myself when I saw how important the Arctic was. Back in the Gore movie, it was already the loss of reflectivity, even back in 2006, was resulting in 20% of global temperature rise. And I just asked myself finally this question of, well, if I just boosted that reflectivity a little bit, what would happen? And we've tried a number of materials over time. The most practical one, really, is this hollow glass beads now. Sheets, oh boy, people have had such problems with sheets over time. A number of people have tried that and not gotten so far as I know on that. But really, the idea is simply that we use enough monolayers of it. We're aiming for about 5 monolayers. We find that at that level, so 5 thicknesses of these rather small beads, gives us a pretty good boost on reflectivity while not piling up tons of material. We seem to be reaching a sort of maximum gain in reflectivity, boost in reflectivity per amount of material that we put there. Mm-hmm. It's as simple as that. I mean, it's really a simple concept.
And how do you apply these glass beads in the Arctic context?
Right, so you saw our test site up on a lake. We don't have sea ice permits yet, remember, on a lake in Barrow, Alaska, in the Barrow Experimental Observatory area, where we work with the Inupiat Eskimos in their science logistics company, UIC Science, to deploy this. And we used a modified drop spreader, agricultural drop spreader, that was modified by a company in Minnesota. We've made lots of friends in Minnesota from working on that lake for years. And just use that to, in a metered way, spread material by dragging that drop spreader behind a snowmobile and just spreading it, in an ever-widening circular pattern to get an even application. And yes, many adventures which we won't have time to go into now. For sea ice, and part of why we know that we need a few years R&D, 3 years is really our best estimate. Once we have the permits, we need to work out exactly how we're going to deploy it from seaworthy ships. And we're thinking that some of the old crude carriers, for instance, might be worthy, Arctic seaworthy, high-capacity vessels to let us get this near the ice, probably late in the season as it's almost melted out, and blow this material over that thin remaining ice there. This is part of what we're asking the climate modelers. What's the best time of year? What's the best area? How much do we have to do that? We'd completely rebuild the tanks. You don't want any crude contamination on this. But that seems to be the method that will be the most economical, least footprint, least GHG generated and such, to be able to get this in the right spots. And we'll be doing that informed by climate modeling, as we always do, monitor very closely, and then feeding back that information to the climate modeling and just that iterative process, make sure we're doing the right job.
Mm-hmm. So is this geoengineering? Are we modifying the Earth?
Well, you could technically call it that. That term has been co-opted by a certain family of solutions that are talking about adding things to the atmosphere. We like to call this, and the AGU, the American Geophysical Union, this year actually separated the streams for the geoengineering solutions versus what we're calling climate solutions or climate restoration, to talk really more about where are we rebuilding something that until recently was a natural, a system that was there. So here we're rebuilding Arctic ice where it has been historically, which, is a restorative path rather than, going down a different path.
Great. Well, thank you very much for helping lay that out for us so we have a better picture of how it works. Let's take a few minutes now before we open it up to the audience to talk a little bit about some of the barriers and the opportunities, right? I know we've had these common themes of talking about policy. You mentioned permitting. We've heard about the need for funding as a key factor for scale. This is a question for both of you. What are your near-term struggles that you're grappling with, and what are the opportunities to overcome them?
For us, it's a race, right? It's a race against time, because the predictions are that we could be ice-free in the summer in the Arctic by 2030, plus or minus 10 years. And that means it could be as early as next year. So it's never enough money, never enough time, really, to just race to get this here. As I say, what we're looking for is pretty modest, to finish out the R&D within the next 3 years, make sure we've got the right methods to deploy. But part of that is developing this governance framework that really should not be developed by the researchers. We can certainly advise, regulatory bodies and get that done. And then beyond that, and we're in very friendly conversations with our own EPA and with the International Maritime Organization and such, but where can we get our first permit for sea ice deployment is an ongoing mission, and we invite all ideas. And then the funding and permissions to go to scale. We don't imagine that we're going to immediately grow into $1 billion per year company to do this. We think that we need to do this in partnership with some international consortium or some single country or the UN in order to go to scale. And developing those relationships is really, really important as well. But it really is a race.
Well, you anticipated my next question in mentioning partners. And you asked the audience here to join you. You mentioned that you potentially would like to partner with a country. What does a partnership look like, you think? I mean, if you said, come join me right now, who would you address that message to, and what would you be asking them for?
Well, to start with, I mean, for right now, it's permission to work offshore, off the coasts of Greenland or Svalbard, the either side of the Fram Strait, or the Hudson Bay, so we could help out the polar bears in Canada, to get our sea ice deployment methods really worked out. Post that, I mean, what we really do need is cooperation. The UN would be ideal, to just make sure that this has been decided by someone other than the researchers themselves. I really think that's important as being in the interests of humanity. And so that's the kind of invitation we have.
So for both of you, a question about this financing. Do you see government, business, or philanthropy taking the lead, or some other category?
Oh, there's such an important point I've been forgetting to make, and thank you. The leverage here, I mean, I can see the insurance industry or people just interested in the interests of humanity. We are a nonprofit. There are probably some for-profit ways to do it. I haven't figured out how to monetize the Arctic, but if you look at the fact that you need such a tiny amount of money compared to the devastation that we are preventing, I would think the insurance industry would have, or just governments, realizing they're going to have to somehow pay for the damages if these things happen, would have a very keen interest in doing that 1,000 to 1 at least leverage of, it's like the person who was speaking, right, Dr. Paul, who was speaking about wildfires. If you set a small controlled burn, you can avoid this horrible devastation. It's that kind of philosophy. Let's do our small intervention so we can prevent a world of damage.
How do you bridge the worlds of science, environmental protection, and entrepreneurship, and bring it all together? How does that work? Do you think about bringing together these different skill sets you have, or it just happens?
You answer it.
Oh, okay.
I do the question.
It's a matter of bringing your best self every day and keep striving to get better, I would say. One of the things I do, which is very useful, is I have a class at Stanford every fall that's called Engineering, Entrepreneurship, and Climate Change. And I get wonderful guest lecturers who come and help me teach that class. And that helps with the outreach of making sure that students and all the auditors who come to Stanford to take this understand there's hopeful solutions out there. And I think that's part of it, is keep yourself, you're staring into a terrible situation, right? And to keep yourself motivated with the fact that there's hopeful solutions helps. And it helps you grow a really wonderful team around yourself, right?
All right, so let's open it up. We'll try to give you an opportunity. I see a hand back there.
Hi, thank you so much. I have just 2 quick questions for Leslie. First of all, what percentage of the Arctic would you have to cover?
Oh, yes.
And second of all, what are the carbon impacts of extraction of silica versus the impacts for sea ice?
Okay. So what we're aiming for as far as the Fram Strait, what we're modeling right now, is 0.7% of the Arctic sea ice. So a very small proportion, right? As far as the carbon footprint, it depends what manufacturer we go with. There are several of making these hollow glass beads, and what process they're using. But it's fairly low footprint compared to what you're doing. You're reflecting, you're really shifting the energy balance of the Arctic. You're reflecting back so much more than you've had. So it's a net win for sure. And I don't really have the number, because it does depend on the manufacturer we use, which process to give you that full footprint. Sorry. And then did you ask another question, or were those were the 2? the area, and, yeah.
Another question here up in front?
Thank you for your inspired work and your presentation, Leslie. This is not a question as much as it's an inspired idea. I think your $5 billion a year should just be a line item in the Defense Department's budget. They wouldn't even feel it, and it's way better national security.
Do you have connections there? Yeah, great, yes.
This gentleman here?
Hi. Sort of a question for both of you because it's a little bit comparable, but do you have an idea of the, say, cost per acre for doing what you're talking about doing?
I have a cost of, and my colleague prepared this for me because I never remember this number, so let me do this. And I've got now the number looked up. It's $5,400 per square kilometer at small volume prices. You can imagine that if we were buying in the sorts of quantities that we actually need, we would be able to bring those prices down.
And that's a single application, once a year?
Yep. I mean, what we're estimating is $1 to $5 billion per year for that 100,000 square kilometers. That is what the climate modelers are modeling. That is that 0.7% of the Arctic. Sorry, brain came back. And so it's just a trivial cost compared to these devastating, other disasters. But we do think it's the conservative assumption should be made that we will need to reapply every year, and maybe in slightly different areas every year, depending how things performed and what the climate modelers are telling us about weather for that year.
All right, any questions from this side? I see a question, gentleman towards the back.
Thanks both of you for your talks. Very interesting idea about spreading microbeads. And I have a question about the potential environmental impacts because these
can you speak
microbeads
louder?
are much. Can you hear me okay now?
Better, yeah.
Better.
Sorry about that. Thanks for your talks. Very interesting idea. I'm curious about the microbeads and the potential environmental impact of them. They're shaped a lot like a nice fish egg, which is a great food item for a variety of grazers or predators. They're going to be released into the water column right around spring bloom when a lot of larval fish are coming to the surface to feed. Have you assessed environmental impacts or looked at those very much?
Yeah, we have. They come up very clean in the manufacturer's material safety data sheets overall. Again, fundamentally silica. We have sent these to outside testing labs to test on representative bird and fish species, and they're finding no issue. But it's something that would, again, it's why we file with regulatory agencies as well and keep thinking about what time of year is best. But we're going to be very carefully looking, are there any untoward impacts? Should we pivot, on material or timing or whatever? Because really, I live by that first do no harm. I mean, so yes, if you have any expertise in this area that you want to help us make sure we're not going to cause an impact in the way we do it, that would be helpful. Think of the harm we're avoiding too, though.
Sure, I'd be curious. Especially if they're floating, then they're going to remain there every time they're ingested and lost. They'll come back to the surface. If they have a microbial film on them, that would change their sort of how attractive they are to a variety of predators. So I'd be pretty careful about trying to assess their potential impacts. But thanks, I'm glad you're here thinking about it.
Yeah, well, we're thinking about it hard. What we have found on the lake that we've gotten to watch the most closely, both those lakes in Minnesota and in Barrow, we watch it getting blown to shore and getting taken up in the mud, and sand. It's just basically like a very foot-friendly sand, if you will. It's
Question over here to my right.
Yeah, hi. Thank you, Leslie. Thank you for your presentation. It's a fascinating idea, but some of those numbers just feel so small. Isn't the whole principle here you're actually lowering the albedo of the whole Arctic, like reflecting back more light? And wouldn't you need to, I don't know, do a lot more?
what we're finding.
Feels way too small.
Yeah, what we're finding from the climate modeling, and it's profound, and I'm looking forward to their finishing this work on the Fram Strait so we can get the paper published out there. But they're finding just profound impacts Arctic-wide, depending which year, which time we're applying it. We're having to work with the phases of the Arctic oscillation, the entire complex weather patterns. But if we're hitting it right, we get this absolutely profound leverage. That's what we're seeing. You know, I mean, the proof will be in the pudding. As you can probably tell from a dozen years of field testing, it's very simple to sit at your desk and assume something, but you've got to really get out there and prove things to make sure it's right, right?
That was kind of my follow-up question. How would you measure it working? I mean,
We're working out some collaborations with NASA for satellite data, you know, ISAT-2, where we've got a number of proposals there to really start getting more worldwide eyes on this. What we do now is we have instrumentation buoys that are monitoring what we're doing on these lakes. And we have, I mean, that is a lot of our work, is getting the right kind of instrumentation and remote monitoring so that we can look at it back from our lab in Redwood City, but then also go up and fly a drone and, you know, really look at this. We're up there a lot when we're testing.
thank you. And one last one. That video was great, but it also demonstrates there's some pretty incredible currents in the Arctic.
They apparently get affected by going ahead and doing this. It's basically a flow restrictor, if you indulge my microfluidics part of my background. So by making ice last longer, you're actually slowing the flow, and it's actually incredibly effective is what the climate modeling is saying. You know, again, the proof of the pudding is proving it out. It's part of why we need this several-year runway to make sure we really, you know, have nailed down the R&D questions. But it's looking incredibly promising. And the climate modeling, again, you don't want to trust the researcher themselves to do their own evaluation. I am really happy that we're dealing with real experts in ice albedo feedback modeling, climate modeling.
Well, I'd like to thank my fellow panelists. Let's give them a hand.
We don't do that.